The ground around Hudson Bay is rising at roughly 10 millimeters a year. Land south of the Great Lakes is sinking a millimeter or two, and the same cause is behind both. Mantle displaced by 3 kilometers of ice, flowing back now into the space the ice used to fill. That ice finished melting about 8,000 years ago. What is moving today is the rock's answer to it, arriving late at the only speed rock can manage. Nobody could have measured that a century ago. A centimeter a year hides inside the ordinary noise of a landscape. Frost lifting soil in one season and dropping it the next, a building settling, a survey marker that shifts because the rock it was cut into shifted. It became legible when receivers were bolted directly to bedrock and left there for years, reporting their own position until the drift separated from the noise and turned out to be running one way. That rate is not only a curiosity. How quickly a continent comes back up after a weight is taken off, it depends on how stiff the material underneath happens to be. That makes the millimeters a measurement of the mantle as well, and one of the few direct handles anyone has on the behavior of rock a few hundred kilometers down. All along, the coast had been keeping the same record, and in the north, it is not subtle about it. Around the eastern shore of Hudson Bay, the old shorelines lie stacked one above another up the hillsides, gravel ridges left by a sea that was there, and then slightly lower, and then lower again. Each ridge is a beach that stopped being a beach, abandoned as the land beneath it lifted clear of the water. You can walk up them, and they climb a couple of 100 meters before they run out. The ridges can be dated too. Shells and driftwood caught in the gravel give a radiocarbon age for each one, which turns the staircase into a rough clock for how fast the land came up. Scandinavia is doing the same thing. The head of the Gulf of Bothnia, between Sweden and Finland, is coming up at close to the same rate. Towns there have had to follow their own harbours seaward as the water pulled back, and a chart drawn 2 centuries ago already shows a coastline that does not quite match the one there now. The weight was ice, and it sat over the bay long enough for the crust to give way underneath it. 3 kilometers of ice is not a dramatic pressure by the standards of the deep earth, but it is relentless, and rock, held under it for tens of thousands of years, stops behaving like stone and begins to flow. The mantle beneath moved sideways to get out from under the load, and where it arrived, it pushed the surface up into a low rim. That rim is what is deflating now, south of the Great Lakes, a long way from where any of it began. There have been cities on this planet for about 6,000 years. The ice over Hudson Bay had already been gone for 2,000 of them when the first one went up, and the ground beneath it is still coming. Ice on that scale has to come from somewhere, and it came from the ocean. Every cubic kilometer of it started as seawater, evaporated off the surface, carried inland on the weather, dropped as snow, and locked into a place it could not run back from. Water that falls as rain is back in the sea within weeks. Water that falls as snow onto a growing ice sheet can be held for 100,000 years. The sea paid for the ice, and it paid in depth. Coastlines moved seaward and kept going, uncovering ground that had been seafloor since long before there was anyone to walk on it. The sun never dimmed through any of it. Light arrived at the top of the atmosphere in the quantity it arrives in now, and what changed was how much of it the ground below held onto. For tens of thousands of years, that light came down onto surfaces that sent most of it straight back up, and the planet stayed cold in broad daylight. None of it is finished. Calling it the last ice age puts the whole thing in a tense the evidence does not support. The rock is still moving, the mantle underneath has not finished flowing, and coastlines are still finding their level. The only reason it reads as history is that you cannot hold still long enough to notice. Both halves of that record survive. The beaches climbing the hillsides in the north are the half that is easy to reach. The other half is underwater, the old coast itself, drowned where it stood, sitting in the dark under a few tens of meters of sea and largely undisturbed since the water came over it. Salt water is not kind to most things, but it works slowly, and a surface that goes under and is then covered by silt can sit for a very long time with almost nothing happening to it. People lived down there. Some of what they left is still lying on the floor where they left it. Getting down to that floor takes a while, so one small thing first. If slow documentaries about the planet's deep past are the kind of thing you want at this hour, subscribing is what keeps them arriving. And I'm curious about one thing before we go. Of the two movements in the opening minute, which one landed harder, the ground going up or the ground going down? One word is plenty, and then we can start. The water over that old coastline has not moved much in 8,000 years. It has been sitting there through the whole of the written record, holding its temperature and its dark, keeping the floor underneath it in roughly the condition it was left in. One stretch of that floor lies under the limestone coast east of Marseille, where the cliffs run straight down into the water and keep going. 37 meters below the surface, the rock opens. The gap is narrow, and behind it, a flooded passage runs back into the headland for 175 meters, climbing as it goes. It has been full of water for something like 10,000 years, which is roughly when the rising sea came level with the opening and went in. Henri Cosquer, a professional diver, went through that gap in 1985 and followed the passage up. 175 meters is not much of a swim in open water. Inside a tube of rock, with the entrance somewhere behind and no surface overhead to reach for, it is a different quantity altogether. At the far end, the passage surfaced into air and into a chamber with a beach in it. Everything known about the cave since has been recovered by people working underwater on a clock, carrying their own air in and their own notes out. That is worth holding on to, because it explains the shape of the record. This is a site that cannot be walked into, cannot be excavated in the ordinary way, and gives up what it has slowly. The cave is half drowned and half dry, and the line between the two halves is the most informative thing in it. Seawater fills the lower galleries and stands at a level, the way water does. What is above that level is more or less as it was left. Below it, the walls have been scoured and dissolved, and whatever they used to carry is not there to be looked at. That loss was not sudden. The sea came up the inside of the cave, the way it came up everywhere else, over centuries. The destruction climbed the walls slowly, a hand's width at a time, taking the lowest images first and working upward until it stopped where it stands today. Limestone gives way to salt water, and charcoal on a wet wall does not last at all. So the cave keeps two records at once: the world the painters were living in, and a horizontal mark left by the sea that arrived long after they had gone, showing exactly how far up it came. The second record was not made deliberately, and it is the more precise of the two. Above the line, something near 500 figures survive, painted onto the rock or cut into it with a point spread through the dry chambers. Most of them are the animals common to European caves of that age: horses, bison, aurochs, ibex, chamois, several kinds of deer, and a big cat that has never been pinned to a species. The rest of the bestiary is what makes the cave unusual. Alongside the horses and the bison, the walls carry seals, fish, shapes that have been read as jellyfish or octopus, and a group of birds generally identified as great auks. A great auk was a heavy, flightless seabird that swam rather than flew, and it belonged to the cold North Atlantic. There have been none anywhere since the 19th century. Its presence on a ceiling near Marseille says something about the water rather than about the painter's taste. Birds of that kind do not range into a warm Mediterranean, and if they were close enough to be drawn from life, the sea below that cave was a good deal colder than the sea there now. The seals are read as monk seals, which are still there, just. They are among the rarest marine mammals left anywhere, and among the very few things on those walls that a person could still go out and see alive. It was also a long way below the cave. When the paintings were made, the shoreline lay out and down the slope, and the entrance that now sits 37 meters under stood high and dry above open ground. If you had walked out of it and looked south, you would have seen limestone and scrub running away for kilometers before it reached anything wet. The arithmetic of that is easier to feel from inside the cave than from a chart. The dry chambers, the ones with the pictures in them, sit at roughly the height the sea has now climbed to. The water standing in the lower galleries has stopped where it stopped. So the artists were working at what is today the waterline, and the sea they could see from the entrance was well beneath their feet, out past a long apron of dry ground that has since gone under, which is why the bestiary reads the way it does. Ibex and chamois live on steep rock, and there was steep rock behind the cave. Seals and auks belong to a cold shore, and a cold shore was what lay in front of it. What is on those walls is a habitat list, and it was drawn by people standing in the middle of it who had no particular reason to think it would ever be anywhere else. Some of the images were made with charcoal, which means they can be dated directly. That is unusual. Most cave art can only be bracketed by whatever happens to be lying on the floor beneath it. The dates from this cave fall into two groups, one at around 29,000 years ago and the other at around 21,000, with a long silence between them. 8,000 years separate the two groups. Nobody in the later one could have known anyone from the earlier or been told anything reliable about them, and they walked into a cave that already had pictures in it. The site is usually given a single age, somewhere around 30,000 years, which is close enough to be useful, and hides the fact that there were two visits a long way apart. That later visit sits closest to this story. 21,000 years ago falls inside the coldest stretch of the whole glaciation, when the ice sheets had reached their furthest extent and the sea had gone as far out as it was going to go. Those painters were working at the bottom of it, and nothing in what they left suggests it struck them as unusual. The auks were simply the birds that were there. The clearest human trace in the cave is not an animal. Dozens of hands are stenciled on the walls, made by holding a hand flat against the rock and blowing pigment around it, so that what survives is the gap where the hand was. The proportions have been measured and read as belonging to men, women, and children, though a stenciled outline is a thin basis for that kind of claim. What the cave does not say is a longer list. It does not say whether anyone lived in it, how often it was visited between the two dated clusters, or whether the images went up in a day or across a lifetime. It says nothing about what any of them were for. The animals can be identified because they are pictures of animals. The reason for putting them on a ceiling that far inside a headland is not recoverable, and it would be very easy to pretend otherwise. The one thing the cave settles, without needing anyone's interpretation, is that a coastline is not a fixed property of the planet. It is a level. It was somewhere else when those pictures were made. It is somewhere else now, and the distance between the two is marked on the wall of that cave where the water came to rest. Marks like that are not unique to one headland in the south of France. Every drowned coast carries one, and when they are surveyed, they agree with each other to within a few meters right around the world. All of them are recording the same thing, a volume of water that was not in the ocean at the time, and that had to be somewhere. Off the south coast of Barbados, a drowned reef terrace sits in water far too deep for anything to have built it there. Reef corals need light. They grow in the top few meters of the sea and nowhere below that, which makes a terrace of them lying 100 meters down a fairly simple statement about where the surface used to be. Coral is also datable to an unusual standard. The skeleton takes up uranium from seawater as it grows, and almost no thorium, and thorium is what uranium slowly turns into. The ratio between the two in a piece of dead coral is therefore a clock, and it started running when the animal stopped. Richard Fairbanks drilled the Barbados terraces in the late 1980s and combined the two measurements, how old and how deep, into the first serious curve of where the sea had been. One site, though, is only ever one site's answer, and the trouble is the one already established further north. Land moves. Any sea level record taken near a former ice sheet is measuring two things at once: the water rising and the ground rising beneath it, with no way to separate them from the record alone. So the useful sites are the far ones, chosen for being nowhere near the ice. Barbados, Tahiti, the Huon Peninsula on the north coast of Papua New Guinea. Even those need work. Huon is rising on its own account, pushed up by the plate boundary it sits on, and the sea floor generally flexes a little as water is loaded back onto it. No single global sea level exists to be gone and measured. What exists is a height of water relative to the land at each particular place, and the figure everyone quotes is an average reconstructed out of hundreds of them. 1,000 records, then, is not 1,000 times more of the same thing. Sites at different distances from the old ice respond differently, and they do it in a pattern that can be predicted, so the disagreements between them stop being noise and start being information. Solve the whole set together, and both answers come out at once: the sea level and the crustal motion, which is what no single site can ever give. That is the reconstruction Kurt Lambeck and his colleagues published in 2014. Roughly 1,000 observations from far-field sites spanning the last 35,000 years, inverted together rather than corrected one at a time. The lowest point comes out at 134 meters below where the sea stands today. It fell slowly to get there, through the 8,000 years between 29 and 21,000 years ago, and then it stopped falling. 134 meters across 8,000 years works out at a little under 2 centimeters a year, which sounds like nothing and is not nothing. Over a single long life, it comes to about a meter of drop. On a shelf that slopes gently, a meter of vertical becomes a considerable distance horizontally. The shoreline kept moving outward the whole time, slowly enough that nobody had cause to remark on it, and fast enough that the map was different by the end. Other studies put the low point higher, at 120 meters or 125. The spread has very little to do with the corals, and almost everything to do with what is done to them afterwards, which model of the flexing crust is used, and which assumptions about the ice go into it. It matters too whether a given paper is reporting a global average or the relative level at one particular coast. Nobody in that literature argues about whether the sea was far lower than it is. The argument runs over the last 10 or 15 meters. A number like that is worth having because it converts into geography. The seafloor has been mapped, and the depth of every point on the shelf is known, so a sea level 134 meters lower can be drawn straight onto the chart, and the old coastline falls out. Somebody has now done that for the entire planet at intervals and published the result as a dataset anybody can open. It is a global average, though, and it does not transfer to any particular coast without care. No individual shoreline simply dropped by 134 meters, because no individual shoreline has held still since. Some have risen, some have subsided, some have been squeezed by the same crustal flexing that made the measurement difficult in the first place. The average is what remains after all of that local behavior has been modeled out, and drawing it back onto a real coast means putting the local behavior back in. Two quantities come out of the work. The first is the water, about 52 million cubic kilometers, taken out of the ocean and held on land as ice. Some of that ice was not standing on land in the modern sense at all. It was grounded on continental shelf that is now sea floor, which is part of why the accounting is awkward, because ice advanced onto ground the sea later took back. The second quantity is the ground that appeared underneath where the water had been, somewhere between 15 and 20 million square kilometres of new coast and shelf and plain. That is more land than South America covers. New ground came up wherever the shelf was broad and shallow, and the broadest shallow shelves in the world are in Southeast Asia and off the north coast of Australia. 4 million square kilometres of Southeast Asia sit in water shallower than 134 metres, which is why, at the low stand, they were not water at all. The Sunda Shelf, which today lies under the Java Sea and the southern reach of the South China Sea, came out almost entirely. Java, Sumatra and Borneo stopped being islands and became high ground on one continuous plain running back to the Malay Peninsula and the Asian mainland. A river system drained that plain northward into what is now the South China Sea, gathering water off all three of the future islands as it went. Those channels are still down there, cut into the shelf and visible on the survey lines, a whole drainage pattern lying under a shallow, warm sea and running toward a coast that stopped existing. You could have walked from mainland Asia out to Borneo and crossed nothing deeper than a river. At the other end of the same shelf system, Australia and New Guinea were a single continent. The ground between them runs more than 200 kilometres across and stays shallow the whole way, so it stood clear of the sea, and the north of Australia carried on into the New Guinea highlands without a break. The vertigo in all this is not really in the numbers. It is in what the numbers do to the picture already in your head. The outline of the continents you learned as a child, the one that can be drawn from memory without particularly trying, is the outline they take at one specific sea level. That level has been where it is now for a small slice of the last 500,000 years. Glacials run long and interglacials run short, so the familiar arrangement is the brief version, the shape the planet holds during its warm intervals rather than the shape it holds most of the time, which leaves the water itself to account for. 52 million cubic kilometres cannot be spread thinly. Poured evenly over every continent, it would stand a few hundred metres deep, which is not how water behaves on land, so it was never lying about as a layer. It collected in a handful of places, nearly all of them in the northern hemisphere, and it grew upward from there until it was standing kilometres thick and going nowhere at all. 4 of those places carried almost the whole of it. The largest lay over North America and is called the Laurentide, after the Laurentian highlands of eastern Canada. It covered essentially the whole of Canada and pushed south past the Great Lakes into what is now the American Midwest. A second, the Cordilleran, sat on the mountain ranges of British Columbia and Alaska and eventually joined the first along its western edge. A third covered Scandinavia, the Baltic, and a good part of northern Europe. The fourth stood on the Barents and Kara Seas north of Russia, which are shelf rather than deep ocean, so that one was grounded on seafloor across much of its extent, holding down ground the water later took back. Of the 4, the Scandinavian sheet is the easiest to get a grip on because it has been reconstructed in more detail than the others. It covered around 4 million square kilometres and held something close to 3.9 million cubic kilometres of ice, which is comparable to what the Greenland ice sheet holds today. Greenland now contains more ice than anything else in the northern hemisphere by a wide margin. 21,000 years ago it would have looked ordinary set beside Scandinavia and small set beside the Laurentide. Over Hudson Bay and the shield rock around it, the Laurentide stood something on the order of 3 to 4 kilometres thick. That is a range rather than a figure, and the reason is worth stating plainly. Nobody has measured it because the ice is not there. Thickness has to be reconstructed from 3 lines of evidence that are required to agree. The margins are mapped from what the ice left on the ground and dated from material caught up in it. The profile has to be physically possible, since ice of a given extent can only pile so steeply before it spreads under its own weight and flattens itself out. and the crust's answer has to come out right, because rock pushed down by a load returns at a rate the load sets. Margins are the easiest part to find, because a stalled ice edge dumps everything it has been carrying in a ridge along its own front. Those ridges are moraines, and they survive, so the outline of a vanished sheet can be walked. Europe's sheet has had that treatment most thoroughly. A compilation called Dated One, assembled by Anna Hughes, Richard Gillenkreutz and their colleagues, gathered the dates from across northern Europe and drew the ice margin where it stood every 1,000 years, from 25,000 years ago to 10,000. It amounts to a sequence of outlines, one per millennium, of something no longer there to check them against. At a single point on that map, the numbers change character. 3 kilometres of ice standing on one patch of Canadian bedrock presses down with roughly the force of 2.5 kilometres of ocean. That is deep-sea pressure delivered to a landscape that had never been anywhere near the sea. By the standards of the mantle, it is a light touch, and the mantle is what eventually moved. By the standards of the rock at the surface, it is absolute. Pressure of that order does something specific to ice. It lowers the temperature at which ice melts by a small amount, but a decisive one. The base of a thick sheet can therefore sit at its melting point and run wet, while the surface 3 kilometres above it is well below freezing. Water gets in underneath. Once it is there, the sheet stops gripping the stone and begins to slide on it. The base of an ice sheet, in other words, does not sit still. Ice, under that much of its own weight, deforms and creeps outward, dragging whatever is frozen into its underside across the rock beneath. The Canadian shield was planed by that process. Grooves run across the outcrops in the direction the ice was travelling, in parallel sets, some fine enough to look scratched with a needle, and some wide enough to deserve the word groove. You can put a hand on them today on bare rock in Ontario and Manitoba. Grooves run across bare rock in Sweden and Finland too, aligned the same way, cut by the same mechanism at the far end of one event. That subsurface water had to go somewhere, and it did not simply pool. It ran in channels cut upward into the ice itself, carrying sand and gravel along the floor of each tunnel and dropping the load as the flow slowed. When the ice finally went, the tunnels went with it, and the sediment stayed. Eskers are what that leaves. Long winding ridges of gravel running for tens of kilometres across Finland and Ontario, tracing the course of a river that had 3 kilometres of ice for a roof. Roads follow some of them, because a dry gravel ridge across boggy ground is the obvious place to put one. You can drive the line of a river that ran under an ice sheet without ever being told that is what it is. Bigger things moved too. Boulders were quarried out of one formation, carried hundreds of kilometres, and set down on ground with no geological relationship to them whatsoever. They are still sitting there in fields and forests, the most obvious evidence in the whole subject. All of that is what the load did to the top of the rock. Underneath, it did something slower and much larger. The mantle moved aside to get out from under the weight. The crust went down with it. And beneath the centre of the Laurentide, the surface was pressed several hundred metres below where it would otherwise sit. Part of that has since been given back. Part of it has not, which is where the reconstruction gets its third constraint. The millimetres coming up through Hudson Bay feed straight back into the estimate of how much ice was there, because the amount of rebound still to run depends on how much was taken off in the first place. The ICE-6G reconstructions and their predecessors are built that way, out of the geology, the ice physics and the crust's ongoing answer, adjusted against one another until they stop disagreeing. Up at the top, a sheet that size has a consequence of its own. Air cools with height at something close to 6.5 degrees per kilometre. A sheet that has grown to 3 kilometres has therefore lifted its own summit into air roughly 20 degrees colder than the air over the ground it started from. it manufactured its own climate. Snow falling on that summit was falling into conditions the same location at sea level could never have produced. That is a loop, and it is worth naming as one. Height makes cold, and cold preserves height. A sheet that grows tall becomes harder to remove for the plain reason that its melting surface is no longer where the warm air is, and every additional meter of thickness lifts the target a little further out of reach. Loops of that kind are straightforward to start and awkward to stop. Warming the lowlands does very little to a surface 3 kilometres above them, which is a large part of why ice sheets, once properly established, are so reluctant to leave. None of it was delivered. Nothing pushed the ocean onto Canada, and no mechanism moved water in bulk from one part of the world to another. Every cubic kilometre of those 4 sheets arrived as snow, one storm at a time, in ordinary quantities, onto ground that would have looked entirely unremarkable in any single winter. The whole structure, 4 sheets and 52 million cubic kilometres and a continent pressed several hundred metres out of shape, is the residue of a small annual surplus. It ran for about 6,500 years, from roughly 33,000 years ago until the sheets stopped growing. Surplus is the whole of it, more arriving in a year than leaving. These were dry places, and they did not get much snow. What mattered was what became of it after it landed, and for 6,500 years across the north of the world, what became of it was nothing. What has to happen to a summer for snow to survive it? Less than the question implies. A winter in northern Canada is already cold enough to snow, and making that winter colder achieves almost nothing, because snow does not much care how far below freezing the air is once it is below freezing at all. The whole question is what happens in July. A patch of last winter's snow either goes or it does not, and the difference between an interglacial and an ice age is which of those two outcomes prevails in enough places for enough years running. An ice sheet keeps a very simple set of books. Snow arrives, snow leaves, and what is still there at the end of the year is that year's contribution. Arrival depends on how much falls, which in the cold, dry north is never very much and does not vary greatly from one century to the next. Departure depends on melt, and melt happens inside a window of a few weeks. Nearly all the variability in the account sits in that window, which is why the books turn on the summer and hardly at all on the winter. Which raises the awkward part. Across an entire glacial cycle, the total energy the planet receives from the sun in a year barely moves. The quantity stays, the arrangement changes. That same annual budget gets parcelled out differently between the seasons and between the hemispheres, and the parcelling runs on 3 separate clocks at periods of roughly 41,000 years, 23,000 and 100,000. Those clocks have been running for as long as there has been an orbit to run them. The first is the tilt of the axis, which is not fixed. It swings between about 22 degrees and 24.5, and back again, on a rhythm of some 41,000 years. A steeper tilt sharpens the seasons everywhere, giving hotter summers and colder winters in both hemispheres at once. A shallower tilt evens them out, and an evened-out summer is a summer that struggles to finish its work. Second is a slow swivel of the axis itself, the way a spinning top wobbles, taking something like 23,000 years to come round. What it changes is timing. The orbit is not a perfect circle, so there is a point each year where the planet passes closest to the sun and a point where it is furthest, and the swivel moves which season those points fall in. At present, the Northern Hemisphere has its winter at the close approach. Half a cycle from now, it will have its summer there instead. Third is the shape of the orbit, which stretches from nearly circular to slightly elliptical and back over something close to 100,000 years, with a longer 400,000-year rhythm folded into it. On its own, it does very little, because the difference in sunlight between a round orbit and a stretched one is small. Its real job is to set how much the swivel matters. When the orbit is nearly circular, the distance to the Sun hardly varies through the year, so it makes little difference which season sits at the near point. When the orbit is stretched, the same swivel becomes a substantial lever. All three operate over the whole planet, and all three get to build something in only one part of it, for reasons of geography rather than physics. Ice sheets need land to stand on. At the equivalent latitude in the south, there is almost nothing but ocean, and ocean will not hold a kilometre of ice. At 65 degrees north, there is Canada, and Scandinavia, and Siberia. So the entire global cycle, the sea level, and the exposed shelves and all of it, hangs on how much sunlight lands on one band of northern continent during a few weeks each summer. That is an accident of where the continents currently sit. The first person to work out that the numbers were large enough to matter was a Scot called James Crowell. He was the son of a stonemason, largely self-taught, in poor health for most of his life and short of money for all of it. In 1859, he took a job as janitor at the Andersonian Institution in Glasgow, a post that came with a library and with hours in which nobody needed him. 5 years after that, at 43, he published a paper in the Philosophical magazine arguing that orbit and axis could between them change the sunlight reaching a hemisphere in a given season by as much as a fifth. A fifth is a great deal. Tyndall read it, and Lyell and Darwin. Crowell's version did not survive contact with the evidence in every particular, and getting the criterion right took another 50 years and an enormous quantity of arithmetic. That arithmetic was done by Milutin Milankovitch in circumstances not incidental to the work. He was on his honeymoon in July 1914, in Dalj, the town he came from, which lay inside Austria-Hungary. Austria-Hungary declared war on Serbia while he was there, and Milankovitch, a Serbian citizen, became a prisoner of war. Pressure from Austrian scientists got him released on Christmas Eve. He was then offered internment in Vienna or in Budapest, and took Budapest, on the grounds that in Vienna everybody was starving. The Hungarian Academy of Sciences gave him the use of its library, and he stayed there until the war ended. What he did with those 4 years was work out by hand how much sunlight had arrived at northern latitudes, season by season, across the previous 600,000 years. No machine of any kind assisted him, and nobody was working alongside him on it. 600,000 years of sunlight, calculated in 4. It convinced very few people, and it did not convince them quickly. Testing the theory required a record of past climate, detailed enough and well enough dated to lay against the curves, and no such record existed until sediment cores could be raised from the deep sea floor and read. When that finally happened, the paper reporting it appeared in Science on the 10th of December 1976 by James Hayes, John Imbrie and Nicholas Shackleton, and it is remembered as the moment the ice ages were solved. Its title said something more careful than that. The orbit was described as a pacemaker rather than a cause. The finding the paper actually reported was narrower than the summary it later acquired. Across the previous 500,000 years, major climatic changes had followed variations in obliquity and precession. Tilt and swivel. The third clock, the shape of the orbit, is the one the glacial cycles most obviously march to, and it is the one the paper could least account for. That gap has a name, and it is not closed. Nobody disputes the pacing, because the cycles sit in the sediment and the ice and the isotopes at exactly the periods the astronomy predicts. The amplitude is the trouble. The strongest signal in the whole record belongs to the weakest forcing on the list, and half a century of work has not produced an explanation everybody accepts, which is where the amplifiers come in, and the first of them is visible in any photograph of snow. Fresh snow returns something like 80 or 90% of the sunlight landing on it. Tundra wet rock and open water return less than a fifth of it and absorb the rest, which is to say they turn it into warmth at ground level. So the loop runs like this. A summer slightly too weak to clear the snow leaves a white patch where there would otherwise have been dark ground. That patch rejects sunlight the dark ground would have absorbed, which leaves the air and soil around it a little colder than they would otherwise have been. Colder air and colder soil make the following summer slightly less capable of clearing the snow, which leaves a slightly larger white patch. Then it goes round again. Nothing in that sequence is dramatic on any single pass. What it has is direction. Every turn leaves the system marginally more inclined to do the same thing next time, and a process with a direction and 10,000 years to work in has no need to be fast. All of which accounts for the growth and accounts for it in the right place. It does not account for the size. Ice and albedo make a local argument. They work where there is ice, on ground where snow can lie. Inside the band of northern land, the tilt and the swivel are acting on. The cooling was not local. It reached the tropics, where nothing was white and no ice sheet came within thousands of kilometers. Something else was moving at the same time, something that needed no land to stand on and took no notice of latitude, and it was moving through the only medium that touches every part of the planet at once. On the high plateau of East Antarctica, at a place called Dome Sea, a drill went down more than 3 kilometers and brought back 800,000 years of air. Snow falling on an ice sheet traps air between its grains. More snow lands on top, the layers compact, the spaces pinch shut, and what was open atmosphere becomes a sealed bubble with a date on it. The gas in those bubbles is the old atmosphere itself, kept intact, available to be released and measured. What it says is consistent to the point of monotony. Through the warm intervals, carbon dioxide sits at around 280 parts per million. Through the cold ones, it sits between about 180 and 200. Down in the cold, up in the warm, 8 complete times across those 800,000 years, with the earlier interglacials running a little lower than the recent ones. That number is worth trusting more than most because carbon dioxide mixes. The atmosphere turns itself over in about a year, so a measurement taken at one point on the Antarctic plateau is a measurement of the whole planet's air. Whatever was happening to the carbon was happening everywhere at once, over ocean and desert and forest alike, which is something no ice sheet in Canada could manage. Which brings in the first thing the cold did, before any of the chemistry. Cold air cannot hold water. The relationship is steep and it is not negotiable. For every degree the air loses, its capacity for water vapor falls by something close to 7%. Take several degrees off the planet, and a great deal of the water stops being airborne at all, which means less cloud, less rain, and a very different distribution of what remains. Dry ground with wind across it gives up its surface. The glacial world had a great deal of newly dry ground on offer. Shelves had come out of the sea, deserts had spread as the rain belts moved, and immediately in front of every ice margin lay the outwash plains. Ice grinds rock. The same movement that cut those grooves across Ontario and Finland produced the powder the grooves were cut with, and meltwater carried it out past the ice front and spread it flat. In summer the plains ran braided with water. In winter they dried, and the wind took the fine material off the top. Every ice sheet in the northern hemisphere was manufacturing its own dust and putting it into the air. The ice keeps that record too, in the same layers. Dust concentration at Dome Sea during the last glacial maximum ran at around 800 parts per billion by weight, against about 15 through the Holocene, which is a change of more than 50 times. The deposition rate, the amount actually landing per year, was up by a factor of roughly 25. Greenland's glacial layers hold somewhere between 10 and 100 times what its Holocene layers do, and the width of that range reflects a supply that genuinely came and went, Where all of it came from is less settled than how much of it there was. Antarctic dust has been fingerprinted geochemically and traced to southern sources with reasonable confidence. Greenland's is argued over. East Asian deserts, the Chinese loess, the Sahara and European loess have all been proposed, and recent work on individual particles suggests the source shifted repeatedly on timescales of 1,000 years or so, rather than staying put. The Southern Ocean is where that dust did chemistry. It is a strange piece of ocean. The water welling up there is loaded with nitrate and phosphate, the raw materials of plankton growth, and yet the growth is modest because one ingredient is missing. Photosynthesis needs iron. Open ocean water holds almost none of it in dissolved form, and the Southern Ocean sits a long way from any continental supply, so the nitrate goes back down unused. Dust delivers iron. Some fraction of what lands on the sea surface dissolves, and that fraction is what counts. At the glacial maximum, the soluble iron reaching the Southern Ocean out of the sky was at least 10 times the modern figure, which put it on a level with the amount arriving from below in upwelling water. If you had drawn a bucket of that surface water and set it beside a bucket from the same spot today, the difference would not have been visible, and it would have been decisive. What happens next is the part that moves carbon. Plankton photosynthesize, and photosynthesis takes carbon dioxide out of the water they are floating in. Surface water short of carbon dioxide draws more from the air above it. When the plankton die, a fraction of them sinks, and the carbon in those bodies goes down with them, out of contact with the atmosphere for centuries or for very much longer. Follow that chain to its end, and it arrives back at its beginning. Cold produces dry, dry produces dust, dust delivers iron, iron produces plankton, plankton pull carbon out of the air, and less carbon in the air produces cold. Nothing in that sequence is a figure of speech. Each leg has been measured in something physical, the dust in the ice and the iron in the dust and the carbon in the bubbles, and the last leg feeds the first. Run it a second time and everything moves the same way, only further. A world that has already cooled is drier than it was, so the second circuit starts with more exposed ground and more wind across it. More dust reaches the Southern Ocean. More carbon leaves the air. The world that comes out of the second circuit is colder and drier than the one that went in, which is the condition required for a third. The mechanism stays the same on every pass. What moves is the starting condition, and it moves one way. Iron was not working alone though, and this is where the tidiness ends. Colder water dissolves more gas, so some of the missing carbon went into the ocean for reasons of straightforward physics. Sea ice spread north across the Southern Ocean and put a lid on it, cutting the exchange between the deep water coming up and the air waiting above. The water column itself became more layered, which slowed the return of deep carbon to the surface, and across thousands of years, the chemistry of the deep ocean adjusted to hold more of it. Add all of that up, and the sum comes out short. The whole drawdown is somewhere between 80 and 100 parts per million. Iron fertilization is credited with 20 to 40 of it, which is a real contribution and a partial one. Solubility, sea ice cover, layering, and the slow adjustment of deep ocean chemistry take shares of what is left, and those shares are not independent of one another, so they cannot simply be added together. Several of them are counting the same carbon twice. So the position is this. The number is known to within a few parts per million because it was measured in a bubble rather than inferred from anything. The mechanisms are known individually, and each has been quantified on its own. What nobody has managed is to assemble them into an account that reaches 80 without double counting, and half a century of work has not produced one. Candidate mechanisms are not the problem. Assembling them into a total is. That gap does not get any smaller when the record is extended backwards. That core at Dome C holds 8 complete circuits of the loop, stacked one on top of another all the way down. 8 times the carbon went down, and 8 times it came back up. At the bottom of every one of those descents, it landed on very nearly the same figure, somewhere close to 180 parts per million, as though there were a floor beneath it. Why the floor sits where it does is not known either. What the core does hold is all of it together in the same layers, laid down in the same years. The dust and the gas came out of the same ice at the same depth, and in the tropics, where no ice sheet came near and nothing on the ground was white, the shading effect of the airborne dust by itself was doing about as much cooling as the fall in carbon dioxide was doing. 2 effects of comparable size pushing the same direction over ocean the ice never touched. There is a map published in 1976 of the sea surface temperature of the last glacial maximum. It was made by a consortium called CliMap, and it was the first serious attempt to put numbers on the whole ocean at once rather than at scattered points. The high latitudes on it are dramatically colder than today. The tropics are not. Across most of the equatorial band, that glacial ocean runs about 1 to 2 degrees cooler than the modern one, which is to say barely different at all. That map came out of an ingenious method, and at the time the best available. Sediment on the deep sea floor is largely made of the shells of surface plankton that died and sank. Different species prefer different temperatures, so the mix of species in any layer of that sediment is a statement about the water that was above it. Take core tops from all over the modern ocean, where the temperature is known, and the relationship can be calibrated precisely. This assemblage means 28 degrees, that one means 22. Then go down the core into the glacial layers and read the answer off. The result carried a great deal of weight, and not only because it was the only global map anybody had. A tropics that barely moves while the poles fall by 10 degrees or more describes a stiff climate system, one that resists being pushed. It implied that the planet's response to a change in forcing was modest, and that implication mattered well beyond the study of ice ages. Trouble came from land, and it came almost immediately. Tropical mountains carry glaciers, and glaciers leave moraines where they stopped. Glacial age moraines on the tropical peaks of the Andes, East Africa and New Guinea sit roughly a kilometre below where the ice reaches now. Air cools with height at a known rate, so a snowline a kilometre lower is a fairly direct statement about temperature, and the statement it makes is something like 5 or 6 degrees of cooling at that altitude. For that to sit alongside 1 or 2 degrees at sea level, the air in between would have to have behaved in a way no atmosphere has been observed to behave. Corals said something similar. Chemical measurements on fossil reef material from the tropics pointed to 4 or 5 degrees. So did the first analyses of dissolved gas in old tropical groundwater. What followed ran for the better part of 40 years and did not proceed tidally in one direction. By 2000, a careful review of the whole dispute was picking holes in both camps at once. It questioned how reliably coral chemistry could be converted into a temperature, and questioned the assumption that a snowline a kilometre up could be projected straight down to the sea surface. It proposed something in the middle, around 2.5 degrees of cooling in the warm pool. Nobody simply discovered that CliMap was wrong. The field spent a generation failing to agree on how wrong. The clearest account of what went astray requires nobody to have been careless. A transfer function calibrated on the modern ocean can only return temperatures that exist in the modern ocean. Tropical species already live near the warm end of their range and tolerate a couple of degrees of cooling without the assemblage changing much at all. If the glacial tropics were colder than any water in the calibration set, then no combination of species in that set corresponded to them. The method had nothing to return but the coldest thing it knew. The instrument was reading at the end of its scale. Getting past that took a different kind of thermometer, one that counts no organisms at all. Several exist now. The ratio of magnesium to calcium in a foraminifer's shell varies with the temperature the shell grew in. Certain organic compounds made by marine algae change their structure with temperature and survive in sediment for hundreds of thousands of years. These are chemical measurements rather than ecological ones, and they do not saturate in warm water the way an assemblage does. In 2020, Jessica Tierney and her colleagues assembled a large collection of such proxies and did something unavailable in 1976, which was to combine them with a physics model instead of interpolating between them. The model fills in the ocean where the proxies are silent. The proxies pull the model back wherever they speak. The global mean cooling that comes out of it is 6.1 degrees, with a 95% range running from 5.7 to 6.5. The strongest single check on that arrived a year later from underground. Noble gases dissolve in water, and how much of them dissolves depends on the temperature of the water. At the moment it was last in contact with air. Argon, krypton and xenon take no part in biology and none in chemistry, so nothing that happens to the water afterwards disturbs the record. Rain that fell during the glacial maximum soaked into the ground and worked its way down into an aquifer has been sitting there ever since, still carrying the temperature of the air it fell through. That water is still down there, on 6 continents. Alan Seltzer and his colleagues gathered 4 decades of groundwater measurements from all of them, added new records from the tropics, and put the entire set through a single physical framework. Low-lying land between 45 degrees south and 35 degrees north came out at 5.8 degrees of cooling, give or take 0.6 of a degree, which reconciles the argument. Land cools more than ocean does by a ratio the current generation of models puts at about 1.5. If the ocean's surface came down 4 degrees and the land above it came down almost 6, then a mountain snowline a kilometre lower is exactly what those two figures predict. The mountains had been telling the truth the whole time. What they were being measured against was too low. A third line of work, published the same year, produced a continuous reconstruction running from the maximum to the present at 200-year resolution. The method behind that one has drawn sustained criticism, and the argument is still live. It concerns how much a model should be allowed to shape a reconstruction, and neither side has settled it. None of these figures should be mistaken for a description of anywhere. 6 degrees is a planetary average, arrived at by adding together places that behaved nothing like one another. A noble gas record from continental Europe puts the local cooling there at 9. Greenland was colder again by a very wide margin. Parts of the tropical ocean moved by only 3 degrees, and other parts moved by rather more. The average is a real quantity and a useful one. It is also a quantity that almost no individual place on the planet actually experienced. There is one reason the whole argument was worth 40 years, and it turns on a number that cannot be got at any other way. Climate sensitivity is how much the planet warms for a doubling of carbon dioxide. No experiment produces it because there is one planet and it is not available for trials. What can be done is to find a past state in which both the forcing and the response are known and work backwards. The glacial maximum is the best documented such state in existence. The ice is mapped, the dust is measured, the carbon is in the bubbles, and the temperature is now constrained. Run the arithmetic on 6.1 and it returns a sensitivity of 3.4 degrees. The range on that runs from 2.4 to 4.5. A stiffer tropics would have returned a smaller figure, which is precisely why that map from 1976 mattered to people with no interest in ice ages whatsoever. What the number does not do is describe anything that was alive. An average across a planet is a bookkeeping device, and nothing on the planet was keeping the books. What living things met was a place, a particular latitude and altitude and distance from the ice. Each of those places had its own temperature and its own rainfall and its own length of growing season, none of which had much to do with the global mean. And in the places where the cooling and the drying arrived together, what grew was something the planet does not currently have anywhere. Grass is what grew. It ran from the Atlantic coast of Europe across the whole width of northern Asia, over the floor of the Bering Strait, and on into Alaska and the Yukon, going around the ice sheets rather than stopping where they began. It held that ground for tens of thousands of years, and there is nowhere on the planet now where it can be gone and looked at. Standing on it in July, you would have found something closer to a dry prairie than to anything Arctic. Hard ground, low grass and herbs, almost no trees, and dust lifting whenever the wind got up. Its plants were grasses, sedges, and a high proportion of flowering herbs, which the people who study grassland call forbs. The mixture matters because forbs carry considerably more protein than grass does, and the animals that lived there were large enough to need it. What makes the whole thing awkward to picture is that the same ground is tundra now. Tundra is wet, acidic and mossy, and as grazing land, it is very poor. Nothing moved to make that happen. The latitude is the same and the day length is the same. Only the water is different. Dryness is most of the answer. Water is what makes tundra tundra. Waterlogged ground will not drain, so dead plant material never rots properly and piles up as peat, and peat is acid. Take the water away and none of that follows. The dead material breaks down, the nutrients go back into circulation, and the soil stays mineral instead of turning organic. There was a delivery system as well. The silt blowing off those outwash plains landed on the grassland as readily as it landed in the ocean, and it kept landing year after year, laying down fresh, unweathered rock powder. Ground of that kind is called loess. Its minerals have not been used yet, which is what makes it among the most fertile material there is. What lived on it was a grazing fauna at a scale nothing modern matches: woolly mammoth, horse, steppe bison, woolly rhinoceros, reindeer, and the predators that came with them. The horses are the giveaway. Horses need dry footing and continuous grass, and they do badly on bog. Their bones turn up across the entire span of that grassland, which is read as a statement about the ground rather than about the animal. The name it goes by is the mammoth steppe, and the name is worth pausing over. Steppe is a real word for a real thing, the dry grassland that runs across Ukraine and Kazakhstan and Mongolia, which is alive and can be walked on. Borrowing the word imports that picture, and the picture may not fit. Modern steppe sits in the mid-latitudes, with warm summers and an ordinary cycle of day and night. This ran along the top of the world in continuous summer light and continuous winter dark, on ground frozen solid a metre down all year. Whether that is a steppe or something for which no word exists because no example survives is not a question that can be settled by going to look. How any of it is known has changed completely in about 15 years. The traditional route was bones and pollen, which means waiting for something to have died in the right place and been preserved. The newer route needs no body at all. Everything alive sheds genetic material continuously, in skin and hair and dung, and in frozen ground that material does not break down. A core of permafrost silt therefore holds a molecular census of whatever stood on that spot, layer by layer, in order. A mammoth can be detected without a mammoth being found. Tyler Murchie and his colleagues worked one such core out of the Klondike in the Yukon from ground that is itself loess. 30,000 years of wind-blown silt, frozen where it landed. Reading the DNA down through it gives the vegetation and the animals together on one timeline out of the same material. The archive and the soil are the same substance. A larger study the same year, run out of Copenhagen using soils collected across the Arctic over 2 decades, sequenced everything present rather than searching for particular targets. What came back was a flora that hardly varied. From one side of the Arctic to the other, at the glacial maximum, the plant communities were close to identical, which is not how a modern continent behaves at all. The regional differences that seem so obvious now are Holocene features, and they arrived later. Frozen ground reached a very long way south. In Western Europe, the permafrost margin ran roughly east to west at about 47 degrees north, which puts permanently frozen ground under central France. The margin in that region today runs northwest to southeast between 66 degrees and 52, which is to say nowhere near France. That limit was set by the sea. North Atlantic winter sea ice came down to at least 50 degrees north, and the permafrost boundary tracked it, because no warm water arriving from the southwest meant no maritime air to keep the ground above freezing. If you had walked south from the ice front across Europe, you would have crossed several hundred kilometers of frozen ground before it stopped being frozen. Below that line, the survivors were doing the opposite thing. Oak, beech, hazel, the temperate forest of Europe. None of it tolerates permafrost, and all of it withdrew into the peninsulas, into Iberia and Italy and the Balkans, and into the Caucasus further east. Populations that spend a glacial maximum crammed into a peninsula acquire a distinctive genetic signature, high in variation and full of variants found nowhere else, and that signature is still legible in the trees today. Which refugium mattered most turns out to be a question about mountains. Every one of those peninsulas is closed at the top by a range, and the ranges are not equal. The Pyrenees stand between Iberia and the rest of Europe. The Caucasus is worse. The barriers above the Balkans are the lowest of the set, and when the ice drew back, it was Balkan populations that got out first and travelled furthest. Genetics bear that out in a way that reads almost like a map. Iberian lineages largely stayed in Iberia. Caucasian lineages largely stayed in the Caucasus. Italian and Balkan populations and the rest of Europe show extensive exchange with one another. The most famous refugium contributed the least because it had the worst door. None of the redrawing was confined to the north. Amazonian rainforest, which covers around 80% of that basin now, covered something closer to 40%. The Sahara spread a very long way. Southeast Asia, on all that newly dry ground, was for decades reconstructed as savanna corridors running between surviving blocks of forest. Recent work argues the opposite. Forest mosaics dominated, and open corridors were far less continuous than the older maps had them. The end came between about 13,500 and 10,000 years ago. Reading up through the Klondike core, grasses and forbs give way to woody shrubs, to willow and birch and dwarf scrub, and the animals that needed open ground drop out of the record. 3,500 years, and a biome that had held those latitudes for tens of thousands is no longer there. Which of those two changes drove the other has not been settled. The shrubs may have moved in because the climate turned wetter, and the grazers may have gone because the shrubs took the grass, or the grazers may have gone first for whatever reason, and the shrubs moved in because nothing was left to trample them. The people who published that core set the two possibilities out side by side and declined to choose, which is the correct position and an uncomfortable one. The wider argument about the megafauna sits in a similar state, and it is worth being accurate about how unsettled it is. The Arctic genetic work found humans a minor factor and moisture a major one. Several global analyses of the same period find the reverse, with human arrival explaining the pattern and climate contributing little. A systematic review of the whole dispute published in 2025 concluded that opinion remains deeply divided in exactly the regions with the longest research histories, Australia and the Americas, and that recent claims of consensus, they are premature. Whatever the answer turns out to be, the thing that ended was not a species. It was a working arrangement between grass, dust, frost, and very large animals in which every part depended on the others. The best preserved piece of that arrangement is the ground it was recovered from. Silt that blew off a glacial outwash plain, settled on a grassland, froze and stayed frozen for 30,000 years, holding the genetic traces of everything that walked across it. That ground lies between Siberia and Alaska, on both sides of a strait that was not a strait at the time. Between the Lena River in Siberia and the Mackenzie in Canada lay about 3 million square kilometres of country that never had an ice sheet on it. Not at the glacial maximum, and not in any of the maxima before it either. Ice covered most of the Arctic every time the cycle came round, and every time it went around this, which is an odd thing for the Arctic to do. The obvious expectation is that the coldest ground collects the most ice, and Beringia, the name given to that country, taken from the strait in the middle of it, was as cold as anywhere on the planet. Its interior still records some of the lowest winter temperatures found outside Antarctica. The reason has nothing to do with temperature. An ice sheet is snow that failed to leave, and before snow can fail to leave, it has to arrive. Beringia's problem, from the point of view of building ice, was that almost nothing arrived. Moisture in that part of the world comes off the North Pacific. Standing between the Pacific and the Beringian interior are the Alaska Range and the Brooks Range, and air crossing a mountain range gives up its water on the way up and comes down the far side dry. Everything behind those mountains sat in a rain shadow, and a rain shadow at that latitude produces a desert that happens to be frozen. Following the mechanism through is worth the trouble, because one piece of weather produced two opposite results. Air coming in off the Pacific is loaded with water. Forced up the windward flank of a range, it cools, and cooling air cannot hold what it was carrying, so the water comes out as rain low down and as snow higher up. By the time that air crests the range, it has been wrung out, and coming down the far side it warms again. Warm, dry air arriving over cold ground takes moisture rather than delivering it. So the same storms that starved Beringia buried the mountains standing in front of it. The Cordilleran ice sheet sat on the ranges of British Columbia and Alaska precisely because that is where the snow was being taken out of the air. A few hundred kilometers further inland, the same weather system delivered a desert. That arrangement held through every glacial cycle of the Pleistocene, which is to say for something over 2 million years. The ice came and went around it each time. The mountains did not move, the Pacific stayed where it was, and the ground behind them stayed dry. What the country was actually like can be read off a list of things it did not have. No trees anywhere, of any size, no bogs, almost no standing water, not a lake worth the name across most of it, in a landscape where the ground was frozen solid a meter down. That last absence is the sharp one. Frozen ground normally makes wetland because water cannot drain through it and has to sit on top. Tundra is waterlogged for exactly that reason. For Beringia to be frozen and dry at the same time, the water arriving each year had to be scarce enough that the ground could evaporate it away before it pooled. Walking across that country in summer, you would have gone a long way between drinks. What grew there was that same dry grassland, and Beringia held the least interrupted stretch of it. Low, deep-rooted, grazed hard, under skies that were clear more often than skies at that latitude have any business being. Which brings up the word. Almost everyone who has heard of this place has heard of it as the Bering Land Bridge, and the phrase does something specific and unhelpful to the picture. A bridge is narrow, and it is a way of getting from one side to another rather than a place to be. The word carries a destination at the far end, and some urgency about reaching it. None of that describes what was there. At its widest, the ground ran about 1,600 kilometers from the Arctic coast down to its southern edge, which is further than the distance from London to Rome. 3 million square kilometers is roughly the area of India. Nobody crossed it in the sense the word implies, because it was not a crossing. It was a country with its own weather and its own vegetation and its own animals and eventually its own people, and they lived on it for generations at a stretch without going anywhere. The second thing the phrase gets wrong is when. The strait itself is shallow, 50 meters or so, which by oceanic standards is nothing, and which means the gate opens and shuts on fairly small movements of sea level. That makes it tempting to assume it shut early and stayed shut for as long as the world stayed cold, and the sediment says otherwise. Nor was it only the strait that came up. The Bering and Chukchi shelves on either side are broad and shallow across an enormous area, so a fall in sea level does not simply narrow a channel, it takes the sea off a region. The shoreline moves hundreds of kilometers, and what appears is a plain rather than a causeway. Shallow also means twitchy. On ground that flat, 10 meters of sea level shifts the coast a very long way, so the difference between a strait and a subcontinent comes down to a few tens of meters of ocean. That is why the gate has a date at all, and why the date is reasonably sharp instead of smeared across several thousand years of gradual narrowing. Pacific water reaches the Arctic Ocean through that one opening and no other. It carries a chemical signature Arctic water does not, so the presence of that signature in a dated Arctic core is a direct statement about whether the strait was open when the layer formed. When the signal is there, the gate is open. When it stops, the gate is shut and the ground is dry. Jesse Farmer and his colleagues ran that record and published it at the end of 2022. The strait was open water from at least 46,000 years ago until roughly 35,700. It closed, in other words, only about 10,000 years before the glacial maximum. That result comes from one study using one tracer. It has not yet been reproduced by an independent method, and until it is, the date carries the weight of a single line of evidence rather than several, which is a reason to state it carefully, not a reason to set it aside. It is the best constrained answer anyone has, and it moves the timing by a very long way. So the land had a start date. It came up out of the water around 35,700 years ago, stayed up while the sea stayed down, and went under again when the melt arrived. Something over 20,000 years from first dry ground to last. Long enough for a great many generations, and short enough that the whole of it fits inside the span of a single glacial cycle with room to spare, which is the constraint that matters for anyone who was standing on it. There was no era of Beringia reaching back into the deep past, and no long, unhurried drift of populations across a permanent isthmus. There was a gate that opened late, a country behind it that lasted a few hundred generations, and then water again. Anyone who was going to cross had to do it inside that window, and the window is a great deal narrower and a great deal later than the phrase has ever suggested. If you had lived on that ground, nothing about it would have hinted that it was temporary. Stand on the flats at White Sands in southern New Mexico, and there is not much to look at. Gypsum sand, white enough to hurt in strong light, drifting into dunes across a closed basin with mountains around it. What you are standing on is a lake bed. Nothing drains out of that basin. What rain falls in it sits there until it evaporates, and the mineral it leaves behind is the sand. 23,000 years ago, the same basin held a lake, not a deep one, a broad, shallow sheet of water with a wide, muddy margin that advanced and retreated with the season. That margin is the part that matters. Mud at a lake edge is a recording surface, and for a few thousand years it was recording. A footprint is a peculiar kind of evidence. A bone establishes that an animal existed, and a tool establishes that somebody made something. Footprints establish that one particular individual was in one particular place, moving in a particular direction at a particular speed. They also establish that the mud was exactly wet enough to take an impression and exactly dry enough to keep it. They record a few seconds. Nothing else in archaeology has that resolution, and almost nothing else has such poor odds of surviving. The print must be made in the right consistency of sediment, dried without cracking, buried by the next layer before wind or water or another animal destroys it, and then left alone for as long as it takes. Essentially, every footstep ever taken, including all of yours, has failed at least one of those conditions. White sands holds a great many that did not. Human tracks in trails rather than isolated impressions, and in the same deposits the tracks of the animals sharing that lake margin, the large grazers and the things that hunted them. They lie in the sediment together at the same levels, which is a statement about coexistence requiring no interpretation whatever. Part of why the site carried so much weight is that a footprint is difficult to argue with. A stone tool can be picked up and carried, dropped into older sediment by a burrowing animal or a flood, or turn out on closer inspection to be a naturally broken rock. A print cannot be moved without being destroyed. It is made in place at the moment the layer forms, and it stays in that layer or it stops existing. Whatever age the layer has, the print has. Matthew Bennett and his colleagues published the dating in Science in September 2021. Seeds lying in the layers above and below put the trackway surfaces between roughly 23,000 and 21,000 years old. That falls inside the glacial maximum during the coldest stretch of the entire cycle, with the ice sheets at their furthest extent and the sea 134 meters down. The problem this created is one of geography. The two great ice sheets of North America met along the eastern flank of the Rockies. The gap between them is the ice-free corridor that generations of textbooks have people walking down, and it did not become passable until somewhere between 13,800 and 13,000 years ago. That is close to 10,000 years after somebody was walking around a lake in New Mexico. A discrepancy of that size guarantees the dates will be tested hard, and they were. The seeds Bennett's team used came from a submerged aquatic plant, a pondweed called ruppia, and aquatic plants have a known failing as clocks. Radiocarbon dating works because living things take up carbon from the air in a known proportion, and the clock starts when they stop taking it up. A plant growing underwater does not take its carbon from the air, it takes it from the water, and water in a basin like that one arrives through old rock, carrying dissolved carbon millions of years old with no radiocarbon left in it at all. Any plant built partly out of that carbon looks older than it is. How much older depends on the mixture, and the mixture cannot be reconstructed 23,000 years after the fact. That was the correct question to ask, and answering it wrongly would have taken several thousand years off the result. Answering a reservoir problem means dating something that never had one. Pollen from conifers comes off trees, and trees take their carbon out of the air like everything else on land. Pollen out of the same layers as the seeds would give an independent age with none of the same vulnerability. The difficulty is practical. Pollen grains are microscopic, and radiocarbon dating needs a measurable quantity of pure material, which means separating an enormous number of individual grains of one kind out of sediment full of everything else. It is slow work. Jeffrey Pagati, Kathleen Springer and their colleagues did it, and published in Science in October 2023 alongside more than one independent line of evidence. The conifer pollen came back at 23,400 years, plus or minus 2,500. At the other end of the sequence, it gave 22,600, give or take 2,300. Two entirely different materials taken out of the same beds with completely different ways of going wrong and no shared assumption between them, returned the same answer. That settles one thing and leaves another wide open, and it is worth being careful about which is which. The presence is now well supported. People were in the interior of North America during the glacial maximum, at a date that survived a specific and serious technical challenge and was retested using a method chosen precisely because it could not fail in the same way. One consequence of that date runs straight into an argument left standing elsewhere. If people were in the interior 23,000 years ago, and the large animals did not go until the end of the Pleistocene, then the two shared the continent for something close to 11,000 years. A long overlap is harder to reconcile with a rapid arrival and collapse than a short one. It settles nothing, and it changes the shape of what has to be explained. How they got there is not settled at all. The corridor is out for these particular people on straightforward arithmetic. It opened far too late. What remains is the coast. The Pacific margin of the continent carried continuous ice at high latitude and open ground further south, and moving along it by water rather than over land removes the corridor problem entirely. Proposals for when that was possible cluster into two windows, one around 24 to 22,000 years ago and one around 16 to 15,000. Stone tool forms turn up around the whole Pacific Rim in a distribution that fits a coastal spread, and the genetics tie the earliest Americans to Pleistocene populations of northeastern Asia. Trouble with the coastal route lies in where its evidence would have to be. A shoreline camp from 23,000 years ago sat on a beach, now lying 134 meters underwater and some distance out from the modern shore. Whatever those people left is on the continental shelf under the Pacific, in exactly the places nobody can survey easily. The route with the best logic has the worst preservation, which is a reason the argument has stayed unresolved rather than an argument against the route. So the position, stated as carefully as the evidence allows, current findings are consistent with an inland route, with a coastal route, or with both operating at different times, and none of the three can be rejected. There may well have been more than one arrival. Nothing requires the peopling of two continents to have been a single event. What is not in doubt is the ground in New Mexico. Somebody walked across wet mud at the edge of a shallow lake in a basin ringed by mountains, while 3 kilometers of ice stood over Hudson Bay, and the Mediterranean shoreline lay kilometers out from where it is now. If you had walked that margin alongside them, the mud would have taken your print in exactly the same way and lost it inside a season. The walking took a few seconds. It has been kept for 23,000 years. Between 26,500 years ago and 19,000, nearly every ice sheet on the planet stopped advancing. Ice at that thickness never actually stops moving. It flows under its own weight, whatever the climate is doing. What stopped was the outward growth. The margins reached their furthest positions and then held them for something between 7 and 7,500 years. Writing is about 5,000 years old. That plateau outlasted the entire written record of the species with 2,000 years left over. It produced nothing that would show up in a record of any kind, because for the whole of that span, the arrangement of the world did not change. This is the part popular accounts of an ice age tend to skip, and the skipping is understandable. There is a story in the advance, sheets growing, sea level dropping, the map redrawing itself. There is a story in the collapse. Between them sits a stretch longer than either, in which the interesting thing is that nothing was happening at a rate anyone could have noticed, and a stretch like that is difficult to narrate. It is also most of the duration. If the last glacial cycle is going to be described as an event, the event was mainly this. A question follows from all of that, and nothing in the story of the advance answers it. Everything driving the ice outward was a loop that reinforced itself. Snow surviving a summer made the next summer colder. A sheet growing taller lifted its own surface into air that was 20 degrees colder than the ground it started from. A drier world made more dust. The dust took carbon out of the atmosphere, and less carbon made a world colder and drier still, which made more dust. Every one of those gains on each pass, which is more or less the definition of a runaway. So what stopped them? The first answer is the least satisfying and the most important. Nothing stopped them. What was pushing them stopped pushing. Summer sunlight at northern latitudes had been falling for tens of thousands of years, and somewhere in the middle of that plateau, it reached the bottom of its swing and began, very slowly, to come back up. Orbits do not run in one direction. The tilt swings and returns, the swivel comes round, and every quantity they govern has a minimum and passes through it. Those loops were never self-starting. They were amplifiers on a signal, and when the signal stopped falling, the amplification stopped gaining. A second answer is geometric. Every glacier and every ice sheet has a line across it where the snow arriving in a year exactly equals the ice lost in the same year. Above that line it gains, below that line it loses. An ice sheet spreading outward is spreading toward warmer latitudes, so the further the margin travels, the more it has to give back every summer, and the harder the interior has to work to replace what went. Push the edge beyond the point where the interior can resupply it, and it simply melts back to that point and sits there. The position is not chosen. It is the only place the books balance. Third comes the ice itself, which cannot be stacked indefinitely. Ice deforms under load, and the thicker a sheet becomes, the faster it spreads sideways. Adding snow to the top of a 3-kilometre dome mostly makes the dome wider rather than taller. Thickness has a ceiling built into the material. The fourth answer closes back on everything that came before it. Cold air carries less water. A world that had cooled by 6 degrees was delivering markedly less snow than the world which started the process, and an ice sheet is built out of snow. So the same drying that filled the atmosphere with dust and pulled carbon out of the sky was, at the same time, cutting off the supply to the thing that had caused it. The aridity making the Southern Ocean bloom was starving Canada. One mechanism, running one way, with opposite consequences, depending on which end of it is being looked at. Put together, those four produce a plateau rather than a peak. The reinforcing loops were still running throughout, the albedo still rejecting sunlight and the dust still falling into the Southern Ocean, and they were being met by limits that strengthened the further the system went. A balance struck that way does not sit on a knife edge waiting to be tipped. It settles, and it stays settled, and small disturbances get absorbed instead of amplified. 7,000 years of that produced almost nothing anyone can date. The shape of the cycle as a whole is worth keeping hold of at this point. Roughly 6,500 years to build, 7,000 or so to hold, and then a collapse taking a fraction of either. Terminations run consistently faster than inceptions across every cycle in the record and by a wide margin. Part of the reason sits in the channels available. An ice sheet can only gain mass one way, by snow falling on it, and snow falls at the rate the atmosphere can deliver, which in a cold, dry world is not fast. It can lose mass several ways at once, melting at the surface, melting underneath, flowing off into the sea, and breaking up there. Building requires a single slow process to run without interruption for thousands of years on end. Dismantling only requires any of several faster ones to start. There is a caution attached to all of this. Nearly every ice sheet is doing real work in that opening sentence, because the sheets did not all reach their furthest extent in the same century or in the same millennium. Some peaked earlier and some later. The phrase last glacial maximum is a convention drawn around a cluster of dates rather than a single global instant. Even the moment is an interval, none of which means the world was inert. 7,000 years of ordinary weather happened inside that span. Storms crossed the ice, rivers ran off the outwash plains every summer and froze again every winter, herds moved and were followed, dust rose and settled. Something in the order of 280 generations of people lived and died on that landscape, and the great majority of them never saw the arrangement they lived in alter in any way they could have registered. Everything already described was in place at once and stayed in place. The Mediterranean cave stood high and dry above a shoreline that lay kilometres out and several tens of metres down. The grassland ran unbroken from France to the Yukon. The lake in New Mexico filled and shrank with the seasons and took prints along its margin. All of it held together for the whole of that span, and none of it was going anywhere. If you had been born at the start of that stretch, and someone else at the end of it, the two of you would have described the same world, the same coastline, the same ice front, the same animals standing in the same places. 280 generations apart, with nothing in between worth reporting. That is what a stable state looks like from the inside, and stability of that kind is always conditional. It holds while its conditions hold. One of those conditions was a quantity of summer sunlight that had reached the bottom of its range and was, by the ordinary mechanics of an orbit, already on the way back up. There was nothing abrupt about the first 4,000 years of it. Northern summer sunlight passed the bottom of its swing and started back up, and the ice sheets began, very gradually, to give ground. Margins that had held their positions for 7,000 years moved a little. Sea level, sitting near its lowest point, began to rise. Somewhere between 19 and 20,000 years ago, the accounts stopped balancing and never balanced again. The onset left a mark of its own. The sea, which had barely moved for millennia, put on a rise sharp enough to show up in the record as a step rather than a slope, and then the retreat settled back into something slow. Losing an ice sheet is easier than building one because the dismantling has more than one route open to it. They are worth going through one at a time because between them they account for the whole of what followed, including its speed. The first is the one that built the thing, running the other way. Fresh snow, of the kind that falls on the top of an ice sheet, returns most of the sunlight landing on it. Bare ice, once the winter's snow has gone, returns considerably less. Meltwater standing on the surface returns almost none at all, because water is dark. So a melt season that gets slightly ahead of itself darkens the surface it is working on, and a darker surface absorbs more of the next day's sun. Going up, that loop needed centuries to shift anything, because snow accumulates slowly and a white surface stays white. Coming down, it runs inside a single summer. Same feedback, same direction of gain, entirely different clock. Water made at the surface of an ice sheet does not stay on the surface. It finds crevasses and shafts and works its way down, and where it reaches the bed it does what water under ice always does, which is separate the ice from the rock. A sheet already sliding on a wet base slides faster when more water arrives. A sheet sliding faster delivers more ice to its own edges, which is where it is warmest and where the losing happens. At those edges, if the edge is in the sea, the ice does not have to melt at all. It floats, breaks, and leaves. Icebergs remove mass at a rate that has nothing to do with air temperature and everything to do with how quickly ice is arriving at the water, and there is no matching process on the other side of the ledger. Nothing delivers icebergs to a continent. The most consequential route has a name and a fairly exact description. Where an ice sheet meets the sea, there is a line, the grounding line, landward of which the ice rests on rock and seaward of which it floats. How much ice pours across that line depends steeply on how thick the ice is at the crossing. Take a bed that slopes downward inland, which is a common arrangement and was the arrangement under a great deal of the ice in question. If the grounding line retreats even slightly, it moves into deeper water. Deeper water needs thicker ice to stay grounded. Thicker ice at the line means more ice crossing it, which means the sheet behind is losing faster, so the line retreats further, into water deeper still. That is the loop, and it is called marine ice sheet instability. It has a property the other routes lack. Once it starts, the geometry supplies the push. No further warming is required to keep it running. It is not automatic, and the exceptions matter. Beds are not uniformly sloped, and a rise in the rock can stop a retreat dead. Floating ice shelves press back against the ice behind them and hold it up, so a margin with a shelf in front of it is braced. Friction along the walls of an outlet does much the same. Whether any particular margin runs away depends on the shape of the ground beneath it, which is why identical physics produces collapse in one place and stability 100 kilometers along the same coast. Hudson Bay is the case that mattered most in the north, and it is a case the ice made for itself. The floor of that basin lies below sea level, pressed there by the weight of what was standing on it. An ice sheet that has driven its own bed several hundred meters down has excavated a place for the ocean to get into, and the deepest part of the excavation is in the middle. None of this would carry much weight if the mechanism existed only on paper. Grounding lines are surveyed now by satellite repeatedly in the places where they are moving. How fast a line retreats across a reverse-sloping bed, how discharge responds to thickness, what happens to a glacier when the shelf in front of it goes. These are measured quantities now, with error bars attached. They are not inferences drawn from 20,000 years away. The physics used to explain the collapse can be checked against something happening while the checking is done. The collapse itself has a name and a set of dates, and both came out of coral. Reefs cannot keep pace with sea level rising faster than they can grow. When they fall behind, they drown, and drowning leaves a record. A reef surface abandoned at one depth. A new reef started further up the slope. Cores taken off Tahiti during a drilling expedition in 2005 went through exactly that sequence, and the uranium clock in the coral put dates on it. Pierre Deschamps and his colleagues published the result in 2012. Global sea level rose by somewhere between 12 and 22 meters, beginning 14,650 years ago and finished by 14,310. Under 340 years from start to end, which works out at something in the region of 4 centimeters a year, sustained for 3 centuries. Then it stopped, and the stopping is as much a part of the mechanism as the start. A geometric instability runs for exactly as long as the geometry keeps supplying it. Once the grounding lines had backed off the reverse-sloping ground and onto beds that rose inland again, the push went out of it, and the rate dropped to something the reefs could keep up with. 4 centimeters a year does not sound like much. Across a single long life, it comes to nearly 3 meters of vertical rise, and on any low-lying coast, 3 meters of vertical moves the shoreline by a distance nobody could fail to notice. For the 7,000 years before this, the position of the sea had been the one thing about the world that could be relied on absolutely. The pulse took less than a 20th of that span and raised the ocean by up to half of what it eventually took to drown the mouth of a painted cave in the Mediterranean. It coincides with a jump in temperature recorded in the Greenland ice, the warming that opens the interval called the booling. The records do not separate the two cleanly. That is the usual difficulty when two things happen at the same moment and each is capable of causing the other. Where the water came from is the part still open. Tahiti sits a very long way from any northern ice sheet, and distance is the point. When an ice sheet melts, its own gravitational pull on the surrounding ocean relaxes, so sea level close to it rises less than the global average, and sea level far away rises more. The pattern recorded at a far-field site therefore carries information about which sheet the water left. Tahiti's pattern points to a substantial contribution from the south, which was not the expected answer, since the northern sheets held far more ice. It establishes that Antarctica took part. It does not settle how the total divides, and the division has been argued over ever since. One thing the pulse does not record is the route. 52 million cubic kilometers of ice does not run to the sea in a straight line, and it does not go all at once. A great deal of it was held up on the way, ponded behind the ice that was still standing, in lakes with no natural basin, no permanent outlet, and no business existing at all. One of them filled the mountain valleys of western Montana. At its greatest extent, it held about 10,400 cubic kilometers of water, which is not far short of Lake Superior. Nothing held it in place except a lobe of ice sitting across the mouth of a valley in northern Idaho. An ice dam is a poor structure for the job. Ice floats, and water deep enough will lift the ice holding it back, work into the gap, and enlarge whatever channel it finds. The enlarging is the dangerous part. A trickle through a dam of rock stays a trickle. A trickle through a dam of ice melts its own walls as it goes, so the opening widens while the water is running through it, and the flow accelerates as it widens. The failure is not a leak that gets worse, it is a leak that takes the dam apart in a matter of days. Then, the ice advanced again, and the valley closed, and the lake filled up once more. The evidence suggests this happened around 40 times over roughly 2,000 years, which averages out at one flood every 50 years or so. A person living downstream could have seen two of them. Their grandparents would have seen others. Not all of the lake went at once, either. Individual outbursts are estimated to have released up to about 2,000 cubic kilometers, a fifth of the full stage, and quite enough for the purpose. Peak discharge is a modelled quantity rather than a measured one, and the estimates span a wide range, somewhere between 2.75 million and 13.5 million cubic meters per second. Even the bottom of that range is over 1,000 times what the Columbia River ordinarily carries. The top of it puts the flow at something like 10 times the combined discharge of every river on the planet, running through a few valleys in eastern Washington. What that did to eastern Washington is still there to look at. 30,000 square kilometers of it, a landscape called the Channeled Scabland, and the name is descriptive rather than poetic. You can stand at the lip of a cataract several kilometers across with no river in it and nothing at the bottom but dry rock. Erosion worked in two stages, and the geology of the region made both of them efficient. Eastern Washington is built on old flood basalts, layer upon layer of hard volcanic rock, jointed vertically where it cooled and cracked. On top of that sits loess, the same wind-blown silt that fell across the whole northern hemisphere in the cold. Loess is soft. Water moving at that speed took the loess off in sheets, exposing the basalt beneath, and then began working the basalt apart along its own joints, prizing out blocks the size of houses and carrying them away. The result is channels hundreds of meters deep cut into solid rock in a pattern that braids and rejoins the way a stream does on a sandbar, except at a scale of tens of kilometers. Bars of gravel stand where the current slowed, some of them large enough to be mistaken for hills. Boulders lie scattered across the ground that came from formations hundreds of kilometers away, ferried in on ice and dropped where the water let them go. Missoula was not the only lake in the region behaving this way, and not all of them needed ice to hold them in. Lake Bonneville, in the basin that now holds the Great Salt Lake, filled until it overtopped the low divide at its northern rim, and once water is running across a divide of loose material, the divide starts to lower. That flood went down the Snake River. The mechanism is different, and the outcome is the same. A large volume of standing water finding an exit that widens while it is being used. J. Harlan Bretz walked that country through the early 1920s, mapping it, and arrived at the only conclusion the evidence supported. The channels had been cut by an enormous volume of fast-moving water in a very short time, on a scale nothing in the modern world could match. To understand why the profession refused this, it helps to know what geology had spent the previous century escaping. The discipline had fought its way out of flood geology, out of the practice of explaining every landform by a single ancient catastrophe. The tool it used was the principle that the past should be read through processes observable in the present, running at rates observable in the present. That principle is what gave geology deep time, stratigraphy, and its standing as a science. It worked comprehensively. So a young man arriving with a landscape carved in days by an unprecedented flood was proposing from the inside a return to exactly the thing the field had escaped. The reaction was not superstition. It was the immune system of a discipline working precisely as designed, on the one case where it happened to be wrong. Bretz also had a genuine weakness in his argument, and his opponents were right to press it. He could describe the effect in exhaustive detail, and he could not name the cause. Where does that much water come from? Without a source, a flood of that size is not a mechanism, it is a wish. In January 1927, he presented the case to the Geological Society of Washington. The leading authorities in Pleistocene geology were present, several of them from the Geological Survey, and they took the argument apart in turn. Accounts written by people in the room do not describe a debate. Bretz went home and kept mapping. The source, when it came from somebody else. Joseph Pardee had identified glacial Lake Missoula years earlier, and it was Pardee who eventually produced the evidence that the lake had not drained gently, but had emptied catastrophically. That closed the hole in Bretz's case. It did not close the argument, which continued for decades more through further fieldwork, better mapping, and slow accumulation. What finished it was being able to see the whole thing at once. Aerial photography and then imagery from orbit in the 1970s showed the channel pattern across the full 30,000 square kilometers in a single frame, and at that scale the braiding is not arguable. It is a stream bed. It is simply a stream bed several hundred kilometers across. The Geological Society of America gave Bretz its highest award, the Penrose Medal, in 1979. He was 96. He is reported to have told his son that all his enemies were dead, so he had nobody left to gloat over. 52 years is a long time to be right in public without being believed, and it is worth resisting the temptation to make heroes and villains of it. The people who objected in 1927 were defending a hard-won method against what looked exactly like a relapse, and they were asking the correct question which Bretz could not answer. He answered it eventually, with help. The method survived, slightly enlarged, having learned that a process can be both rare and real. As for the ground itself, almost nothing has happened to it since. The last of those floods ran something over 13,000 years ago, and nothing in the modern hydrology of eastern Washington is capable of moving that rock or filling those channels. The scabland is not eroding in any meaningful sense. It is a landscape that was made in a few days and has been sitting there, essentially finished, ever since. The largest of the ice-dammed lakes, though, was not in Montana. It lay along the southern edge of the Laurentide itself. It was very much bigger, and when it emptied, the water did not go west. How long does it take a warming world to reverse? In the North Atlantic, around 12,870 years ago, the answer appears to have been about 3 years. The interval that opened is called the Younger Dryas, after a small Arctic flower whose pollen turns up in European sediments from the period. In places it had no business growing by then. It ran from roughly 12,900 years ago to 11,700. 1,200 years, during which the Northern Hemisphere sat back down into something close to glacial conditions after 4,000 years of climbing out of them. Greenland recorded it in more than one way at once. Oxygen isotopes in the ice, which track the temperature at which the snow formed, shift to glacial values and stay there. The annual layers thin. Snow accumulation at the summit fell by roughly half and did so within a few years. Layers can be counted individually, so the counting is not an estimate. Whatever happened, it happened faster than an ice sheet is able to smooth over, which is why the record carries a step in it rather than a slope. A second thermometer sits in the same ice and works on an entirely different principle. The top of an ice sheet is not solid. It is tens of meters of porous old snow with air moving through it, and when the surface temperature changes sharply, a temperature difference is established down through that layer. Gases sort themselves by weight along such a gradient, the heavier isotopes drifting toward the cold end. The mixture finally sealed into the ice, therefore carries a record of how large the surface jump was, quite independently of the water isotopes. Run on nitrogen and argon from the Greenland summit, that method puts the younger Dryas around 15 degrees colder there than the same place is now. What carried a change of that size is well understood, and it is a circulation still running today. Warm surface water moves north up the Atlantic. On the way it gives up heat to the air and loses water to evaporation, so by the time it reaches the latitudes of Iceland and Labrador, it is both colder and saltier than it started. Cold, salty water is dense enough to sink. It goes down, returns south along the bottom, and the sinking at the northern end is part of what draws the next surface water up behind it. The heat delivered by that flow is very large, and it is delivered to precisely the region that cooled. Fresh water is lighter than salt water and does not mix in readily. Put enough of it onto the surface of the North Atlantic and it sits there as a lid. Water under a lid of fresh water cannot reach the density it needs to sink, so the sinking slows, and when the sinking slows, the pull bringing warm water north slackens with it. That is where the loop closes on itself. A north receiving less heat is colder. Colder air lifts less water off the sea, and a sea surface losing less to evaporation stays fresher than it otherwise would, which holds the lid in place. Add sea ice, which forms easily on a cold, fresh surface, insulates the water beneath from the air above, and reflects sunlight that would otherwise have been absorbed, and the whole arrangement becomes difficult to shift. None of that heat is destroyed. It simply stops going north, which means it stays in the south. The Antarctic ice records exactly that. A warming of 1 or 2 degrees running at the same time as a cooling of 10 to 15 degrees over Greenland, the two hemispheres out of phase with one another. The name for it is the bipolar seesaw, and it has run many times in every glacial period the ice cores reach. The heat is redistributed rather than removed, so the planet's books balance while the distribution does not. 3 years, then 1200. The ratio is worth sitting with for a moment. A system that reorganized itself inside the span of a single memory, then held the new arrangement for something close to 50 generations. If you had been 40 when it began, you would have been among the last people able to remember the world before it, and nobody born after you would have lived to see it return. What started it is another matter, and the honest description of the situation is an unusual one. The mechanism is far better understood than the cause. The circulation, the freshwater cap, the sea ice, the seesaw, all of that is established, quantified, and reproduced. The initiating shove is not. One proposal has held the field for 35 years. Wallace Broecker and his colleagues suggested in 1989 that meltwater from the Great Lake along the Laurentide's southern edge had been draining south down the Mississippi. Their proposal was that it got abruptly rerouted east through the Great Lakes and out along the St. Lawrence, putting a large volume of fresh water straight onto the sinking region. The mechanism is exactly right. The evidence for it has never been found. A flood large enough to stop an ocean circulation ought to have scoured a path, and no such path through the Great Lakes and down the St. Lawrence has been identified. Brooker, who spent the rest of his career on the problem, wrote in 2006 that our inability to identify the path taken by the flood was disconcerting. In 2010, Julian Merton and his colleagues published something that moves the geography of the question. Working along the Mackenzie system in the Canadian Arctic, they identified gravels and a regional erosion surface consistent with a very large flood, dating to shortly after 13,000 years ago, which is to say at about the right moment. The water on that reading went north into the Arctic Ocean rather than east into the Atlantic. Their own conclusion is worded carefully, and the wording matters. They reject the view that the lake's overflow at that time was solely eastward. That is not the same as demonstrating that a northern flood caused the cooling. What it establishes is that a very large flood happened in the right period along a route nobody had been examining. A third possibility has arrived recently from an unexpected direction. For nearly 2 decades, one of the principal lines of evidence for a cosmic impact at the start of the Younger Dryas has been a spike of platinum in the Greenland ice. Platinum is far more abundant in meteoritic material than in ordinary crustal rock. A 2025 analysis re-examined the chronology of that spike and reports 2 things about it. It arrives roughly 45 years after the cooling began, which is too late to have caused it, and it persists for about 14 years, which is the signature of a sustained source rather than an instantaneous one. That same analysis proposes volcanic sulfate reaching the atmosphere around 12,870 years ago as a better candidate for the initiating perturbation. It is a single recent paper, and it has not yet been through the independent assessment that would make it settled, so it belongs in the account as a recent analysis rather than as an answer. The impact hypothesis itself deserves a fair statement. It was a serious proposal made by serious people, and it produced 2 decades of real work. Sampling, dating, and the hunt for corroborating markers in sediments on several continents. Most of those markers have not held up under scrutiny, and the platinum chronology was among the last strong lines it had. That is what testing a hypothesis looks like when the hypothesis does not survive. So the position, after 35 years of work, comes to this. Something delivered a large quantity of fresh water, or of sulfate, or possibly both, into the northern hemisphere at around 12,900 years ago. The response is recorded almost to the year, in 2 independent thermometers, in the same ice. The circulation that carried it is measured and modelled. The thing that started it has not been identified, and none of the 3 candidates on the table is supported well enough to close the question. It ended much as it began. Somewhere near 11,700 years ago, the cap dispersed, the sinking resumed, the warm water came back north, and the Greenland ice records the recovery across roughly a decade, nearly as fast as the collapse had been. The interruption was over. The ice sheets went back to melting, the water went back to arriving, and coastlines that had paused for 12 centuries resumed their retreat inland. Drag a net across the floor of the southern North Sea, and most of what comes up is what you would expect. Fish, sand, the occasional shell. Every so often, it also brings up a lump of black fibrous material that the fishermen working those grounds had a name for. They called it moor log, and they had been hauling it in and throwing it back for as long as anyone could remember. Moor log is peat. Peat forms in bogs and fens, on land, out of plant material that accumulates faster than it can rot, and it takes centuries to build a metre of it. It does not form on a sea floor. Every lump of it dredged out of the North Sea is a statement that the ground it came from was once a wet, vegetated, entirely terrestrial surface, and that it stayed that way long enough to accumulate. In September 1931, a trawler called the Kalinda was working about 25 miles off the Norfolk coast, over ground known as the Lehman and Ower banks, hauling from a depth of roughly 120 feet. The skipper, a man named Pilgrim Lockwood, noticed a block of moorlog in the catch and, for whatever reason, looked at it properly instead of putting it over the side. Inside was a barbed point made of red deer antler, 14.5 centimeters long, in near-perfect condition. It went to Norwich Castle Museum, where it still is, catalogued under an accession number and a year, 1932.39. For decades it was assumed to be Mesolithic, which is to say a few thousand years old. In 1988 it was radiocarbon dated directly, and the result came back somewhere between 11,950 and 11,300 years before the Common Era. Older than anyone had supposed, and older by enough to matter. It is the first direct date for human settlement on that part of the North Sea plain. It places the person who made it in the warm interval between the great meltwater pulse and the 12 centuries of cold that followed. Working out what that plain looked like took an unexpected route. Oil and gas companies have shot seismic surveys across the North Sea for decades, sending sound down into the sediment and recording what comes back to find structures worth drilling into. Those surveys image everything the sound passes through, including the buried land surface, and the data sat in commercial archives for years before anyone thought to read it for anything other than hydrocarbons. The North Sea Paleolandscape Project mapped 23,000 square kilometres of it that way. Later work under Vincent Gaffney extended the reconstruction to nearly 47,000. What emerges is not a featureless shelf. It is a landscape with river systems running to a coast, lake basins, low hills, marsh, and the estuary of a large river that no longer exists. Which is where the popular account of drowned coastlines tends to stop and where the interesting part begins. The phrase in general circulation is lost world, and the framing that goes with it is loss, a place that vanished, a mystery under the water, sometimes a civilization. That framing gets the significance backwards. Doggerland was not a curiosity at the edge of Europe, it was the middle of it. Low, flat, wet, threaded with rivers and estuaries and coastline, which is to say it was the best land available, the places where fresh water meets salt, where fish and fowl and game concentrate, where anyone with a choice would settle. The same grounds have given up large quantities of animal bone from species that were gone before the water arrived, and the argument about why they went is the one left standing elsewhere. What matters here is simpler. When the sea came back, it took the good land first, because the good land was the lowland. How fast it came back is now recorded in some detail, and by the same Pete. In 2025, Mark Heimer and colleagues published a curve built from 88 sea level markers taken out of North Sea peats, spanning from about 13,500 years ago to 6,000. The figures are corrected for the way the crust beneath was still moving after the European ice sheet came off it. The curve has two accelerations in it. One peaks around 10,300 years ago and the other around 8,300, and at both peaks the sea was rising at 8 or 9 millimetres a year. Between 11,000 years ago and 3,000, global mean sea level came up by 37.7 metres. 8 or 9 millimetres a year is worth converting into something a person could have experienced. Across a 70-year life, it comes to about 60 centimetres of vertical rise, knee height across a whole life. If you had spent yours on that coast, the change would have been real and entirely unremarkable. Nobody living through the fastest phase of that drowning could have pointed at the sea and said it was doing anything unusual. On ground that flat, 60 centimetres of vertical takes the shoreline a very long way inland, which brings up the wave. Around 8,150 years ago, a vast section of the Norwegian continental slope let go. The Storegga slide moved somewhere between 2,400 and 3,200 cubic kilometers of material across 95,000 square kilometers of seafloor. The tsunami it generated ran up to about 20 meters in Shetland and several meters on mainland Scotland. It was real, it was enormous, and it is regularly described as the event that destroyed Doggerland. Recent work from the southern North Sea does not support that. By the time Storegga happened, most of the plain was already gone, and what remained went under afterwards for the same reason it had been going under for thousands of years. The sea kept rising. A tsunami is a terrible afternoon. It is not a mechanism for removing a landmass, and the landmass was already almost removed. A second correction is about who was there. There were no cities anywhere on Earth at any point in this story. The people who painted the cave near Marseille were Upper Paleolithic hunters. The people on Doggerland were Mesolithic. Urban settlement, writing, metal, the wheel, all of it comes later, on the far side of the drowning, on the coastlines that were left. The closest thing to a settlement in the whole submerged record sites off the coast of Israel. Atlit Yam was found in 1984 by the marine archaeologist Ehud Galili, 200 to 400 meters offshore in 8 to 11 meters of water, and it covers about 40,000 square meters. Excavation has turned up houses, paved areas, and long unconnected walls, along with thousands of plant and animal remains and dozens of human ones. There is also a semicircle of 7 standing stones between 1 and 2 meters high and weighing up to 600 kilograms, cut with cup marks and arranged around a freshwater spring. It also has wells, stone-lined, dug down to fresh groundwater. A well is not built to measure anything, and it is nevertheless an extremely precise instrument. The fresh water beneath a coastal settlement floats on salt water that has pushed inland underneath it, and the level it sits at is set by the level of the sea. Dig a well, and its depth records where the sea stood on the day you dug it. A well records a second thing as well, and that one is about people rather than about the sea. It records the moment a village stops being viable. As the sea comes up, the salt beneath comes up with it, and the fresh layer thins. The wells go brackish, and then they go salt, and they do it while the houses are still perfectly dry. The people at Atlit Yam moved to higher ground more than once. They were not fleeing water, they were following water and losing. Around 7,000 years ago, the rise finally slowed. Sea level was still about 10 meters below where it stands now, and the rate dropped to something like 2 or 2.5 millimeters a year. The inflection falls between 7,800 and 7,400 years ago. After that, the coastlines settled roughly where they are and stayed. What that leaves is a particular kind of gap. Everything people did during the coldest and most interesting part of this story, they did on land that is now seafloor, because low ground is where people live, and low ground is what the ocean took. The archaeology of the last glacial world is not thin because those people left less behind. It is thin because the places they left it are underwater, and most of that ground has never been surveyed by anybody. Doggerland was under for something like 7,000 years before anyone worked out it had been there. The drowning took 5,000 years, and the forgetting took less than a lifetime, and if a fishing skipper had thrown one particular lump of peat back over the side, it might have taken considerably longer still. Almost none of the evidence in this account was made on purpose. Air sealed into a bubble because snow happened to fall on top of it, and dust that landed on an ice sheet and stayed where it landed. A footprint pressed into mud that dried at exactly the right speed. A well dug by people who wanted water and had no interest whatever in where the sea stood. Beaches abandoned by ground that would not stop rising. coral that drowned trying to keep up, seismic surveys shot to find gas, and a lump of peat in a net. Not one of those was intended as a record, and that is the strongest thing about them. A record assembled from accidents cannot have been arranged to prove anything, because nobody arranging it knew what it would be asked. The uranium in a piece of coral was not put there to date a shoreline, and the nitrogen in Greenland ice was not sorted by weight to give a second opinion on a temperature. There is a question underneath that worth asking honestly, and it does not have a comfortable answer. Everything known about this world is known because certain things happened to survive, and the things that survive are not a random sample. Ice preserves, permafrost preserves, and so do anoxic mud and dry caves and deep, quiet water. Warm, wet ground does not, and neither does anywhere that has since been ploughed, quarried, built on, or scoured by later ice. A great deal of the glacial world sat in exactly those places, and whatever it held cannot be recovered by any method, present or future, because it is no longer there. What can be said, though, can be said firmly. The pacing of the cycle is established. The tilt and the swivel and the shape of the orbit, running on their own periods, redistributing an unchanged annual quantity of sunlight between the seasons and the latitudes. The response is established. The ice sheets, their extents, their thicknesses to within a range, the 52 million cubic kilometres and the 134 metres. The chronology is established in places to the year. The mechanisms are established and can be checked against processes running now. What all of that adds up to is not really a list of events. It is a set of loops. Snow surviving a summer and keeping the next summer colder. A sheet growing tall enough to manufacture its own weather. Cold making dry, dry making dust, and dust feeding an ocean that pulls carbon out of the air. Fresh water capping a circulation and cutting off the heat that would have dispersed it. A grounding line retreating into water that gets deeper the further back it goes. Every one of those is still in place. They are properties of ice and water and air and rock, rather than features of a particular era, and none of them has been switched off. What changed is the setting they are running at. None of this knowledge is old. The idea that there had been an ice age at all was announced in 1837 and resisted for a generation afterwards. The orbital arithmetic was worked out by hand between 1914 and 1918, then waited until 1976 for a record good enough to test it against. The first deep ice cores came out of Greenland and Antarctica within living memory, and reading DNA straight out of frozen soil is about 15 years old. Several of the dates in this account were published in the last 3 years. The whole picture is roughly 2 centuries old, and a great many of the numbers in it are younger than the people using them. 3 things are not established, and they are worth stating plainly rather than tidying away. The first is the carbon. Somewhere between 80 and 100 parts per million left the atmosphere on the way into every glaciation and came back on the way out, 8 times over in the record that reaches furthest. The individual processes capable of moving carbon out of the air have all been identified, and most have been quantified. What has never been done is to add them into a total that reaches 80 without counting the same carbon more than once. That is not a rounding error at the edge of the problem. It is a substantial fraction of the main quantity, missing from the account of the coldest state the planet reaches. The gap matters rather more than a piece of bad bookkeeping would. This is the best documented case in existence of carbon moving between ocean, air and biosphere at a global scale, with the quantity known independently at both ends and the timing known to within centuries. If the accounting cannot be closed where everything is measured, that says something about how completely the carbon cycle is understood, and not only about ice ages. The second is the temperature. 6.1 degrees of global cooling is the best current figure. It is not an old one, and the figure before it was smaller, and the figure before that smaller still. Each revision has moved in the same direction, which is a pattern worth noticing without overreading. It matters beyond the ice ages because the glacial maximum is one of very few states in which both the push and the response can be measured. That makes it one of the few empirical handles on how far the planet moves when it is pushed, and a number still in motion is a handle still loose. The third is the trigger of the interruption. Something put the Northern Hemisphere back into near glacial conditions in about 3 years, 12,900 years ago, and after 35 years of looking, nobody has produced the thing that did it. Each of those gaps has a shape, and it is possible to say what would close it. The carbon needs either a mechanism nobody has proposed yet, or a demonstration that the processes already on the table overlap less than they appear to, which would allow them to be added up honestly. The temperature needs more proxies from land and from the deep tropics, because that is where the reconstructions still disagree most and where the measurements are thinnest. The trigger needs a flood path that can be found and dated, or a volcanic record that survives the sort of independent testing the platinum chronology did not. None of those is out of reach. Each of them is the kind of thing that gets settled by somebody spending years on a problem nobody else is working on. One question that was open has moved recently. An analysis published in early 2025 examined the timing of the terminations rather than their size, and found a pattern in which of the orbital minima actually bring a collapse on. On that reading, the ones that count are the precession minima arriving while the tilt is increasing, taken at the first opportunity after the orbit has been at its roundest. If it holds, the timing of the last several terminations is not a matter of chance, and the 100,000-year rhythm that has troubled the field for half a century is less mysterious than it looks. It is a single recent paper. It has not been through the years of independent testing that turn a result into a fact. There is one more thing the orbital criterion can be asked, and the answer is worth stating exactly and no further. A study published in 2016 established a relationship between northern summer sunlight and atmospheric carbon that accounts for the onset of the past 8 glaciations. Run that relationship on the orbital configuration of the last few thousand years at pre-industrial carbon levels, and the system comes out close to its threshold. An inception was narrowly missed. Run it forward, and on the same criterion, the next opportunity does not arrive for something on the order of 50,000 years. The same work finds that carbon added to the atmosphere since then pushes that opportunity further out again. That is what the study supports. The recovery, meanwhile, went the way recoveries go, which is unevenly and from the edges. Trees came north out of the peninsulas, and the order in which they arrived is still written into the forests of Europe, in populations whose variation thins the further they stand from the ground where they waited. The steppe did not come back. The land it had occupied went to tundra, and further south to forest. The arrangement of grass and dust and frost and very large animals that had held the top of the world for so long did not reassemble anywhere. Some of the animals took a very long time to finish going. Woolly rhinoceros persisted in northern Siberia until about 9,800 years ago. Mammoth held on there until roughly 3,900, and on an island in the Arctic Ocean until about 4,000 years ago. That puts the last of them alive several centuries after the Great Pyramid at Giza was finished. The radiocarbon record from that island shows no long decline before the end. The population appears to have been getting along, and then not to have been there. The people moved as well, and moved the same way. Communities that had been living out on the shelf went inland as the shelf went under, generation after generation, with nobody experiencing it as a migration. What the record shows is not flight. It is a slow drift in where the settlements sit, which is what happens when the ground beneath the best sites gradually stops being ground. What settled into place was a new arrangement rather than a restoration. Forests where there had been steppe, tundra where there had been grassland, and a coastline in a position nothing had occupied before. The distribution of species that came with it was decided by which of them had been in the right pocket at the right moment. By around 7,000 years ago, the water had stopped moving in any way that mattered. The coastlines settled roughly where they are now, and everything anybody can name was built afterwards, on those coastlines, in the interval that followed. Every city, every written language, every building you could point at. That interval has now run about as long as the glacial maximum did. 7,000 years of a stable arrangement then, and 7,000 years of a stable arrangement now. The whole of what gets called history fits inside a stretch of steadiness exactly the length of the one the mammoth steppe had, none of which was arranged for anybody's benefit. The planet was not working toward this. It ran a set of loops until they met their limits, held the result for as long as the forcing held it, and then took the whole thing apart on the way back. What came out the other side was whatever the physics left standing. What it left standing mostly was the edges, not the great populations in the middle of a range, but the ones already pushed into a peninsula, a mountain valley, a south-facing slope, a pocket of ground that happened to stay livable. The oaks that repopulated a continent came out of the Balkans because the Balkans had the lowest hills to climb over. The lineages that made it were the ones already reduced to almost nothing, sitting in the right place when the ice let go. The same was true of everyone. The populations that came through were on coasts and in valleys, and in the pockets of country that stayed habitable, while the country around them did not. None of them was in any position to know they were the ones who would. That is not a consoling arrangement, and it is the arrangement. Everything alive now, without exception, is descended from something that was cornered and got lucky. There is a particular calm available in that, and it is not the calm of being looked after. It is the calm of standing next to a process that is enormously durable, entirely unhurried, and completely uninterested in the outcome. The planet has done this 8 times in the span a single ice core reaches, and many more times before that, and it will do it again, and none of it needs anybody's agreement. The sun never dimmed through any of it. That was the whole strangeness of the thing. The light kept arriving in exactly the quantity it arrives in now, on the same schedule, and the world underneath simply stopped keeping it. White ground sent it back up again. The ground is dark now, and the light stays. The ice is gone from Hudson Bay and has been for 8,000 years. The rock underneath has not finished coming back. It rises about a centimetre a year, in silence, without effort, and it will still be rising long after every question in this account has been answered or abandoned. South of the Great Lakes, the ground is going quietly down. Across Scandinavia, it is coming quietly up. The shorelines are still finding their level. Somewhere north of you, tonight, a beach is a fraction of a millimetre higher than it was this morning. It will be higher again before the light comes back. None of it needs watching. Rest while it comes up.